the three most common forms of quadratic equations and how to convert between them. We'll start with standard form, the form that we're probably most familiar with. In standard form, you have your f of x or your y on one side equal to ax squared plus bx plus c. Now, instead of being like factored form or vertex form where we use parentheses, everything is expanded out when we're in standard form. Let's jump to the next one, factored form, and look at the equation there. When you're factoring, again, you'll have your f of x or your y equal to your two groups, your two factors, x minus something or x plus something, and then x minus something or x plus something in the other group. Now, for this example, instead of having something like a 2x minus 5, which is possible when you're factoring, imagine something like this here in one factor, and then in the other one, an x plus 1. Now that is a possible situation. I decided to factor out everything. So if I had a 2 here, I would factor out that 2, and inside of parentheses, I would simply have x minus 5 halves. So again, the way that I wrote this out, you could have fractions. So that's just something to be aware of. But if we do assume that we are able to have fractions and our x has no coefficient next to it, or a coefficient of 1, then this a right here up front is going to be the same a that we had in standard form. Let's shoot over to vertex form. We have our f of x or our y on one side equal to our a, and if you remember, our a determines how much how wide and which direction the parabola will face. Then we have x minus h, and that whole group is squared, plus a k. Now, if we're going to be converting between these three forms here, if we're going to go from standard form to a factored form, we need to obviously factor the equation. If we're going to go from a factored form back to a standard form, that's when you use FOIL, the distributive property, to expand each of these groups out into a single expression with no parentheses. Going the other way from standard form to vertex form, you have to start completing the square. We'll talk about that in just a second. Once you're in this form, again, you will have to use foiling, or the distributive property, to expand out this group, collect your like terms, and get back to standard form. So whenever you're converting between these forms, it can be a bit of a process. However, let's go ahead and see what the benefits of each of these forms are, what you can do when you are in any particular form. See where the strengths are and the weaknesses. We'll start with the strengths, so I'm going to skip this solving here when you're in vertex form, because it turns out that solving is not something that's particularly easy to do when you're in vertex form. So we're going to jump straight to the axis of symmetry. Remember that it's always going to be an x equals, and it's always going to be the x-coordinate of your vertex. This point right here, if this is your vertex, the x-coordinate is going to be your line of, the value for your line of symmetry. The best part about vertex form is that it's simply h. Whatever value you have in the parentheses, x minus something, right here, squared, that value is going to be the value that you set your line of symmetry equal to. Similarly with the vertex, it's going to be the point h, k, where k is that term that's outside the parentheses here. So vertex form is really, really handy when your goal is to find the vertex or to find the axis of symmetry. When you're solving, it can be a little bit tricky, so we'll leave that for later. Let's jump all the way to the other side. If you are in factored form, that is something where solving is actually particularly easy to do, because all you have to do is set each of these parentheses, each of these groups, equal to 0. So if you have x minus something in your parentheses, well, x is just going to equal that value. Imagine for a second that you would have x equals x minus 3 in here, in this group. If you did, then one of your solutions to the problem is going to be x equals 3. Simple as that. If you had x plus 5 in the other one, well, what's going to make that go to 0? It's going to be a negative 5. So x equals negative 5 would be your second solution. Remember that I have it written here as minus, and when you have plus, you could have x minus a negative 5. That's another way of visualizing that. If it's x minus a negative 5, then x equals negative 5. Makes sense that there should be a solution for that. Clean that up here. So whenever you're solving or finding the roots, that's something that factored form is particularly good at. And again, if you are looking for what those mean, whatever solutions you get, the point, in our case, in our example, we have 3, so the point 3, 0 would be one of the points on your x-axis, and negative 5, 0 would be the other one, using the example numbers that we just had. The whole idea is that your roots are your x-intercepts. They're the points at which your parabola will cross the x-axis. And that's easiest to solve when you're in factored form. When you're in standard form, neither the vertex nor the solutions or roots are particularly easy to find, but there are handy formulas that allow you to do both. So let's go ahead and start with the quadratic equation. Whenever you're in standard form, you can use that big ugly formula in order to find your roots or your solutions. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember to keep your fraction bar all the way across because it is over the entire thing. There's a second way to solve it when you're in standard form by completing the square. Now, completing the square will give you the exact same results as the quadratic equation. So if you are checking your answers or need to have another perspective of how you find these solutions, you can technically use either method and you should get the same results every time. But if we're going to complete the square, let's go through the steps. The first one is to divide by the coefficient of x squared. So divide everything by a in this example. Second step is to get the variables on the left and the constants on the right. So in this case here, we get our x squared and x terms over on the left side of the equation. We get our constant, our c, over on the right side by adding or subtracting terms. Then we complete the square. That's where we have our, go ahead and write out a quick example here. If you have an x squared plus 3x on one side equal to something else on the other side, we're going to say, what is half, actually, let me go ahead and pick an integer value. I didn't pick the 3 is going to be a little bit tough. So let's say you have x squared plus 4x equals 2 here. Now, half of 4, we always take half of our b term. So half of 4 is going to be 2. And then we square that. 2 squared is going to be 4. So we're going to say plus 4 on both sides. And that's how we are able to complete the square. Now we have to factor our variables on this side. So if we're going to factor that, we're going to have x plus or minus something and x plus or minus something. If we did everything correctly in this first step, all we'll have to do is take half of this middle term. So if this is 4, half that middle term is going to be 2. So we have x plus 2, x plus 2. We'll combine that into x plus 2 squared. And then take the square root of both sides. So this other side here is going to equal 6. You take the square root of both sides, and then you would solve for x. And we're not going to go ahead and work through this. The focus of this isn't necessarily learning how to complete the square here, just realizing that completing the square is one technique that you can use to solve something when it's in standard form. Now, one formula that you should be familiar with is finding the axis of symmetry when you're in standard form. That's the negative b over 2a equation. So x is equal to negative b over 2a. And because the value here for your axis of symmetry is going to be the same as the x-coordinate of your vertex, we can also copy that down here. Let's imagine that you found this value to be 2. So if you found this x-coordinate here to be 2, then when you are solving for the y-coordinate of your vertex, you need to plug that 2 back into your original equation. So everywhere you have an x, you need to replace it with a 2. So that means you would have whatever your a value is times 2 squared plus whatever your b value is times 2 plus c. So again, that's where you take whatever value you get for this x-coordinate and you plug it back into the original equation in order to get the y-coordinate of your vertex right here. So there's a few steps involved. It's not the easiest thing to find, but compared to finding it in factored form, it's a little bit easier. So negative b over 2a, plug it back into your equation. We'll go back to factored form. Now we're looking at some of the things that you're very unlikely to find, but just for the sake of consistency and seeing it across all of them, I'm going to include it. So at this point, none of these things that I'm going to show you are things that you would need to memorize or necessarily know, but it can be helpful just to see how it does connect across the 3 forms. So your axis of symmetry, always going to be x equals. Now your axis of symmetry is what divides the parabola in half. So if you're looking for what divides it in half, you may notice that your 2 roots, your 2 x-intercepts, your 2 solutions here, are equally spaced from that axis of symmetry. Because of that, you can actually take the average of your 2 roots. You can add them together and divide by 2, which is just finding the average if you wanted to find your axis of symmetry. So once you know your 2 roots, your 2 x-intercepts, taking the average should be the same as your axis of symmetry every time. And because the axis of symmetry, that value is going to be the same as the value of the x-coordinate of your vertex, you can drop that same answer and plug it in here. And finally, just like we did here, where we took whatever value we got for the x-coordinate and plugged it back into the original equation, you do the same thing here. You take whatever you get for x and plug it back in for y. So that's how you would go from your axis of symmetry value that you found by averaging those 2 x-intercepts into the vertex. Last thing I'm going to show you, we're going to jump way back over to vertex form. And let's imagine that we're finding the solutions. And remember, when you're finding your solutions, you set y equal to 0. So that means this term here is going to go to 0. I cross that out there. So this side of the equation is equal to 0. If you were to do that and you wanted to solve for x, you would subtract k from both sides, effectively eliminating k over here and leaving a negative k on this side of the equation. You would divide both sides by a, canceling that out. You would take the square root of both sides so that you can cancel out that square. You always have to remember your plus or minus here. And then your last step, you would add h to both sides so that x would be all by itself. So if we add h to both sides, and apologize for writing in not the easiest to follow format in this limited space here, but we added h to both sides, effectively canceling that out, so we have x all by itself. That's what we're going to get when we finish completing the square. So when you're in vertex form, half of the work of completing the square has already effectively been done for you. So whenever you have that, if you need to find solutions from something that's already in vertex form, you can continue to complete the square and end up with this equation. I would never try to memorize this equation, but this is something that if you went through the final steps, the factor variable or the square root of both sides and solve for x steps of completing the square, you will find that it's very easy to get back to whatever this equation is to find the solutions or roots. So hopefully this was helpful in getting an idea of how the different forms that we've seen of quadratics all fit together. There are very few new things that we introduced at any given stage when we were talking about different quadratic equations. You'll recognize the three forms as things that come up a lot. But again, look at them each for their strengths. When you are trying to find the roots, find the x-intercepts, being in factored form is one of the best ways to do it because it's so easy to solve for each factor to set each one equal to 0. When you're trying to figure out where the vertex is, being in vertex form is a huge strength because all you need to do is take the value of h and value of k and you're done. The benefit to standard form is that you can do either using a fairly straightforward equation that can help you out. So you'll use either the quadratic formula or the x equals negative b over 2a to do most of the heavy lifting for finding either solutions or the vertex, depending on which one you're looking for. Again, remember on an exam that you don't always have a choice of which technique to use, but when you are given a choice, when it just says solve, find the easiest path to solve. When it just says find the vertex, find the easiest path to the vertex. Make sure that you're converting between forms correctly, whether it's through foiling, factoring, or completing the square. And hopefully this will benefit you as you go forward.